Good afternoon.
Howdy.
Thank you all for coming. As I always say, it's an honor to be here. This is my first Freaknik was in 2011 at the Days Inn, long since gone now. And it's a pleasure to be speaking here.
We had nothing to do with that.
I got a t-shirt that says otherwise.
It was gone.
I'm Jonathan Ryan. I've got a company in Laverne, which is called Swamp's Diesel Performance. Swamp is an old nickname from a truck I built years ago. We specialize in Ford diesel pickup trucks just because I bought one years ago and I want to know how it worked, and I started messing with it. And this is where I've ended up with it 22 years later. We full service shop. Pretty much anything you need done on a truck, we can do it. Is the long explanation. The short answer is I play with trucks and I make them go fast. I'm not an engineer or an electrical engineer. Might be a hacker, and I'm definitely a tinkerer. I like to take things apart and figure out how they work. I started doing this out of just plain curiosity. I had an injector driver module that had failed, and I opened it up and looked inside and saw all this stuff, and I had no idea what any of it was. It was almost kind of like scary. It's like, what is this stuff? Is it going to zap me if I touch it? What's going to happen? From childhood, I knew what a resistor and a diode and a capacitor were. I knew that red goes to positive, black goes to negative. You mix them up and you get sparks, and if the smoke gets out, you can't put it back in. That is all I knew when I started messing with electronics in '06. I want to lay that as a background so you understand where I'm coming from, and that this was self-taught, self-exploration, just plain curiosity. The tools and equipment I started using on this was what I had handy. It was a flatbed scanner, just an ordinary Brother or HP multifunction print, scan, copy device we had in the office. I first tried taking pictures, like photographs of the circuit boards, but it gave too much distortion. I found the scanner gave me a very flat, uniform image. I use a digital multimeter. I've got some drafting software, particularly I'm using one called AutoSketch, which is made by AutoCAD. It's now discontinued. I'm not using that because it was the best, it was just simply what I had at the time. Magnifying glass, or a good lighted magnifying visor, because you're going to be dealing with a lot of really small stuff. A soldering station. When I started this, I had a POS 40-watt Radio Shack soldering iron that was really all it would do is burn the pads off the circuit board. I now have some very nice Metcal stuff. A toaster oven, we'll get into that later on. Documentation, the more info you can come up with about the board you're working on, the easier your job is going to be. For me, it's the manufacturer's wiring diagrams and connector views of saying what pin on this computer goes to what circuit in the vehicle. So I know, oh, this is an input, this is an output, this is an analog sensor, this is unused, undocumented, whatever. The biggest tool here is going to be time and perseverance and patience. This is not a quick, easy way to do anything. There is no quick, easy way to do this. Starting out, 2 identical circuit boards helps a lot. That gives you one to take apart and work with, and another one that can be your reference back to, like, oh, how did that work? What was that part that was here? This is, on this project, this is the computer out of this is specifically an '02 Ford diesel excursion or a California emissions pickup truck. They look pretty much the same 99 through '03, pretty much the same circuit layout, just a couple little differences depending on what they wanted to do. This is the internal strip bare board out of the case. These come coated with a protective conformal coating, which makes everything difficult. It has to be removed. The only way to get it off of these is toluene type solvents and a brush, and a lot of times scraping it off. You need to take anything off the board that sticks up more than about ½ an inch. So to get the flatbed image, I need to take off this capacitor, I need to get the board out of the case, and I need to desolder the header connector on there. Keep everything for future reference. You have no idea how many times you're going to need to go back and say, oh, what was that component, or what was that part number, or what did this thing do? All this stuff is out of Ford trucks. Ford is in a position they can go to Intel or Motorola or Texas Instruments or anybody and say, hey, make us an integrated circuit that does such and put this obscure part number on it that has no data sheet, no reference, anything. So a lot of the stuff that I have to do here is not figuring out just what the part is, but what is it actually doing. If it's got a part number on it, you look up the data sheet and you know, oh, that's a flip-flop or a buffer or a MOSFET driver or something. On this stuff, it was not quite that easy. You need a scanned image of the board. The better the quality of the image and the more precisely you align it, the better it's going to be. Because you're going to be taking multiple images and laying them on top of each other throughout this. And if they get skewed, you're going to end up with stuff that doesn't line up, and it just simply doesn't work. Align the board on the scanner as square as you can possibly get it. You can tape a straight edge or a square to the glass and then tape the board to that so it won't move when you close the scanner cover. My scanner won't scan unless the cover's closed. You're going to scan one side of the board, and then you're going to flip the board over, get an image of the other side. This is the scanned images of that board. On the left we have the top of the board, as I call it. On the right we have the bottom of the board. And you see at the top of it where I've removed the header, you see all the solder holes there. Actually, let me back up to that. On these images, if you look here, I've got these white standoffs that I glued onto the board to keep it a consistent height above the scanner so the image wouldn't get distorted. Then you're going to import that scanned image into your drafting program. I always start with the top of the board, the part with the most components on it. Put the image in a drawing layer by itself, lock the air so the image doesn't move in relation to what you're going to draw on top of it. If stuff does start moving around, it will be a mess. Then create a new layer, and that's what you can actually start the drawing of the circuit on. Hopefully your drawing program has a large library of electronic components to give you a starting point. If it doesn't, you're going to be doing a lot of symbol creation. I started out using as much of the pre-made stuff as I could, and as I went on and kind of refined the technique, I found it better just for a lot of this. I'd use the existing symbols and then I'd modify them to get exactly what I wanted. Like on this board here, there's 4 or 5 different sizes of resistors. So I want in my schematic, I want to tell me not only what the value of the resistor is, but also what size it is. And that way, by having a different symbol for each size resistor and each different value of resistor, when I'm looking at the finished schematic trying to repair a board, I know, oh yeah, it's this size resistor, it should be that value. I can go up my parts bin, bang, I got it, I can fix it. Or if I'm turning it over to one of my technicians, for him to work on it, same thing. He's got the full picture of what it is. Example of some of my symbols, be an NPN transistor, MOSFET, PNP transistor. This round one, that's what I use for a via, which is where the circuit, the trace will cross through one layer of the board to another side of the board. This is a test point, which are for what they call a bed of nails to go onto the board. We can measure the resistances and the voltage between the various parts of the circuit. I use a little red dot to tell me that location on the board is 5 volts. I use the larger red dot that is 12 volts. I've got ground symbols to mark the grounds. I've got them angled because so it keeps minimize stuff from overlapping. These are just some of my little capacitor symbol here. Sorry, I clicked on it. These ones here are what they call a SOT23 package, small outline transistor. It's a little guy about the size of the Lincoln's ear on a penny. I made these schematics up so when I'm looking at it, or a technician is looking at it, he knows exactly, not just that's a diode, but exactly what type of a diode is, what the polarity is, how it's laid out. Here's smaller capacitors, and the stuff I'm dealing with here, the capacitors are strictly for filtering. If this was radio frequency stuff, knowing the exact value of the capacitor would be imperative. Here is just they're just there to clean up a little bit of the electrical noise that's in the circuit. I do need to know exactly what the resistor value is. That is critical in this. These are some footprints, just generic footprints for integrated circuits. Here I have blank solder pads for places where they have the ability to have a component there, but they didn't put anything there on a particular board. They've got that there so they can use one basic circuit layout, but get multiple vehicle functions from one printed circuit board. Next step is placing the components on the image. So on the left, I've got the scanned image. You really can't see it here, but I've been placing components on top of that image exactly as they would be found on the circuit board. If I turn the image off, That's what you see on the right. You can see where I placed the items on there. On this one, this is a separate PCB which is soldered onto the main PCB. This is the barometric pressure sensor. When this was designed, nobody made a reliable, repeatable analog output pressure sensor. So this chip here is the pressure sensor. This is an amplifier which they use to compensate. They made each one unique, and then they compensated for the variation from the pressure sensors. So when it goes in a truck on the computer, every computer is getting the same voltage at the same pressure. That was a hard one to figure out because with all this proprietary stuff on here, it's like, who makes this? What is it? What does it do? How does it work? So I go through the whole board, placing the components on top of it, or on top of the image. Well, one of the things that happens here is they run the circuit traces underneath stuff. And that's why I can't put the circuit traces on yet, because a lot of them, I can do some of them, but then I'm gonna have to go back and find out where the ones that disappeared under a component, where those traces went. After placing all the component symbols on both sides of the printed circuit board, you're ready to strip the board bare. I put it in a toaster oven, which never gets used for food. Again, I heat it up until the solder starts to melt. I take it out and I go whack, and everything blows off. It's like so freaking easy. Take a little solder braid. There'll be some smears of solder, a little desoldering braid to clean up the smears, and it's good to go. Then to make another scanned image of the bare board. And this is where the alignment is critical, because if these two images don't match, all the components you put on the first image aren't going to line up on the second image. And especially if stuff is rotated, that's where it gets really difficult. Try to rotate an image a 1/4 degree and then shift it to the right a little bit and then stretch it a little, get everything to line up. It's just hard. Now I make a new drawing file. And I start with a file, I get to where I need it, keep that one, I go to a new one, a new one, a new one, so I can always step back in different places in the process depending on what I need to see at a given time. I'm going to set the bare board as a background image. I'm going to copy the components I placed on the first image, I'm going to put them on the second image. So now I got all my components on the image with no components on it. There's a fair bit of adjusting, realigning, resizing, because stuff just never comes out exactly right. And some of the distances I'm dealing with here to get the stuff to line up a 10,000th of an inch can throw stuff off. On the right, same image of components before. On the left, this is the board without any components on it now. Now I can see where everything goes. Right here, you can see this is an example of where some circuit traces ran under one of the integrated circuits. Went underneath it, goes to a via, and drops through the other side of the board without taking the integrated circuit off. I've got no idea where it goes. Then start drawing the circuits, and this is painstaking, tedious work. You want a really comfortable to hold mouse, you want a good monitor, you want a comfortable chair, and you want a lot of time to draw every one of these out. There's no easy way around that. But as you can see now, it's starting to look like something. That was the top of the board. Now I do the bottom of the board. Now it's time to tie the top and the bottom together. I'm going to copy the schematic. I'm going to take the schematic for the bottom of the board. I'm going to flip it. I'm going to lay the top schematic on top of it. So on the right, this is what the bottom of the board looks like when I'm actually looking at the bottom of the board. That's what you see here. On the left is what it actually looks like if I'm looking down through the top of it. I got to get them both so they work together. So I take the image on the bottom, mirror it or flip it, depending on what your program calls it. That's what you see on the left. Now on the left is the schematic for the top of the board in green. And one observation here is that, oh, all the traces run left, right. The bottom is in blue, all the traces run up, down. That's just how the designers did it, so they can get from one part to another without things crossing they can't cross. And this is on the right in the blue, that's the bottom image flipped. So if you were Superman with X-ray vision, that's what you'd be seeing on the bottom. The next step is to combine the two. I'll lay the top on the bottom, so now I'm getting basically a complete schematic of how everything ties together. And let's jump here to the bottom. Jump away from the presentation of this is the actual live schematic viewed in AutoSketch. So what I can do here is I can start zooming in and see what's going on, how these different things will relate together. And at this point, it's very hard on the eyes because everything is overlapped, it's scattered over. It is like, how does this all go together? So this is the combined image. And I have two of those. I'll have one that's looking from the top down for when I'm working on the top of the board, and then I'll take that and flip it over, so I've got one looking from the bottom to the top if I'm working on circuits on the bottom of the board. My brain doesn't deal real well with flipping stuff over. So at this point, it's a jumble. It's just an absolute cluster. Next step is I'm going to start grouping stuff together. In this schematic, I grouped it according to pin number. On the connector for the computer, there's 104 pins. From the forward wiring diagrams, I've got the information telling me what's unused, what's the barometric pressure sensor circuit, what's the map sensor circuit, what's the injection control pressure sensor circuit, what's the accelerator pedal input, what's the output for this, where's the transmission shifting functions go to. And so I'll group everything together by the pin where it comes in, which sort of, in this case, it's a very, for what I'm doing, it's a very logical grouping. So I'm going to select all the components that relate together, I'm going to group them, and then I move that to its own layer so it's out of the way. During the grouping process, you may find traces that go to a via and just stop. Okay, it's on the top, there's a via, nothing on the bottom side. These are traces that run inside the board. This board had maybe a dozen of them, which isn't too bad. Some boards have more, some don't have any. You just need to be aware that you have to know where it goes. If you don't know where it goes, who knows? In my schematics, the ones that go inside, I don't know how it runs. I just know it runs from point A to point B. I put those in red on the schematic. To find those, let's see if I can submit this in my pocket. I made up a little copper brush of some desoldering braid crimped into a butt connector that would slip onto the end of my multimeter probe. So I put on the continuity check, and I can just sweep that back and forth across the board, and when it beeps, okay, I know it's there, and then I'll narrow that down with the point of the multimeter. When I first started doing this, I had no idea that stuff ran in the middle of the board. I had no idea that every integrated circuit had a power and a ground. I had no idea about any of this, and now I know it's like, oh, okay, well, I know there's going to be a power and a ground, and this might be more than one, but I know it's going to be here, so I can look for it. When I identify the power and grounds in this method, then I'll go through and put my component symbols on there so I know, oh yeah, this is a 5 volt, this is 12 volt, this is something else. Once the circuits are grouped, then you can start to separate them out to see individual functions and kind of narrow it down. This is the DPC 422, that's the part number or the model number of this circuit board. Circuit 95 and 96. Means it comes in at pin 95 and 96. CID FDCS is cylinder identification, and field delivery command signal, which is the control signals from the computer to the injector module telling it when to fire the injectors. For this part, I'm going to jump back to the AutoSketch program so we can see a little more detail. So on the top, here we can see there's a pin called EF, CID, FDCS. On the FDCS, I got a green trace, so okay, that's on the top of the board. Comes down to a via, there's a capacitor. trace goes to blue, so it's running down the bottom of the board. Comes through a 100K ohm resistor down here, where it's going to tie into these other larger power resistors. We've got some smaller switching transistors in here, gate drive buffers, some over voltage protection diodes, and then it moves over to what's basically a NOR buffer circuit that actual is handling the signal in and out. So the nomenclature on here, the TI 74009, that's the part number on it. I just gave it a number, IC9, for my own reference. I'll label the pins as I figure out what they are, so I don't have to just trace the circuit. I can look at it and go, oh yeah, that pin goes to CID and FDCS. This pin here goes to integrated circuit 1, pin 74, which is the main processor. So that's that circuit as it looks on the board with no distractions. But to really get into this, I need a little more, I need to clean that up, make it a little more user-friendly. So what I'll start doing is basically untangling the circuit and straightening out the traces and shortening the lines and get everything in much more of a, I guess call it like a logical layout as you'd have it if it was an actual electrical schematic. This view here gives you more of a functional equivalent or a functional representation of how it works. So if you were the technician working on this and you've got this like, okay, I may not know exactly, these parts may not be in the same place, but I can see, all right, this is how that circuit's going to work. I put my oscilloscope on it, I see what it's not doing, I know what part of the component to go in to try to fix it. And I'll make notes on here as I'm going along, especially so when I turn this over to my electronics technicians for them to actually take over production. So they've got some idea of what in the world does this do, because they're electronics technicians, not gearheads. They know electronics work, but they don't know how the truck works. So a lot of this to them is going to be complete Greek. Here I've got IC9 again. Pin 1 on it connects to all kinds of different places on the board. Here we've got an input from the main microprocessor, we've got a ground pin, we've got an output through the, what do you call it, through the big resistors out the main pin on the connector, another input from the microprocessor, another output. This same chip, the TI 74009, also controls the glow plug relay, which is handled by another input from the microprocessor. We've got a pin that's not connected, a couple grounds, more connections to the microprocessor, and another. IC2 seems to do absolutely nothing. It's like, what are you doing there on the board? Shown here, that, okay, it's a 5-volt contact there. Here's a view of the microprocessor, where all the stuff I'd had identified at this stage of the game, what the different circuits are. So this is another one that's made by Intel specifically for Ford. I've been able to buy them, but there is no data sheet in existence on just about any of this stuff. The boards I've done with the Word data sheets, oh, life was so easy. so much easier. So that's a sub-circuit. That's what we were seeing before. On the computer that I've been showing you, pretty much all the circuits there were very straightforward input-outputs. There were no logic circuits. There's nothing complex there at all. One of the other ones I did, it had a whole bunch of different buffers and gates and flip-flops and stuff like that. And to make that a little more intelligible for the electronics technician. Get this right again, sorry. Keep trying to click on this to zoom in and I can't. So to make that a little more intelligible for electronics technicians, I've broken everything down a step further and laid it out as you would actually have it on a real electronic schematic. The stuff I'm doing here is more of a hybrid between a schematic and a circuit board trace. And just a little more background, if If you ever do a Google search for a 58 volt FICM, which is a fuel injection control module out of a 03 to an 07 Ford diesel pickup truck, that was, basically that was my hack. They originally came out at 48 volts, and I got to think, wait a minute, what's going to happen if I step up the voltage here? And it worked very nicely. There are now, there's probably 100 companies out there selling them, which is like, hell yeah. That was my hack. I'm proud of that. I'm very proud of that. Questions, comments?
How many did you break in this process?
Oh, God. I've gotten better at that, but you want to have more than one board to start with. And that's where the stuff I'm dealing with is where these are readily available. That's easy. A book I want to tell you about. Came across this book 2 years ago. It's called The Art of PCB Reverse Engineering, subtitled Unraveling the Beauty of the Original Design. This guy, his methods are very different from mine. A lot of the stuff he does is, one example he gives was a, let's say, a multi-million-dollar military radar system where one part of it stopped working. He cannot take that apart and strip that board because otherwise the whole thing's junk. So a lot of what he's doing is going in and tracing out just the part of the circuit that isn't working and making the schematics on that. It's much higher stakes on that. The stuff I'm doing here is, I can buy junk circuit boards for $50 a piece. So you don't want to start this at home with your own car computer. And when I was first doing, when I had no idea about any of this, a lot more stuff got destroyed because at one point it's like, I'm getting this idea that the circuit board has multiple layers, but it's like, how do I get into these inner layers so I can trace them out? And I've tried, heating boards up until the actual, it starts to like delaminate. Whew, that stinks. Smell of burnt electronics, and that didn't work. I was like, okay, this ain't gonna work.
Have you tried like inductance or some kind, or like putting some kind of tone on the traces that go through the vias in the middle of the PCB and trying to stick it out that way? Or have you tried possibly putting high voltage on that trace and then looking at it with a clear camera to see if you can see where the trace goes? Or I mean, can you elaborate on those?
No, I have not. But I got Flir makes a little pocket camera now that goes on a smartphone.
Yeah.
And I got one of those, which was incredibly useful for $250. It paid for itself like in the first week of identifying circuits that were hot.
Yeah.
I've not tried that.
Yeah, I was trying to just use TTL logic or just having a logic analyzer and just looking for it, putting a signal line and just looking for it. But I found putting like inducing like a tone on that trace and then having the other side of the ground and then just having a tiny little needle snipper and just listening for that peak, that chirp, you can find it, kind of know where it goes in the area.
Yeah, I've been doing this the hard way. So that's all I can say. So there was nothing easy about this. It was my own curiosity that I found, hey, wait a minute, I can fix this now. Which is where it really led on the fuel injection control modules for the 03 to 07 trucks. We have sold, I think, in the neighborhood of like 11,000 of those. The injector driver modules from the earlier trucks, I think we're up to like 3,500 or 4,000. The computers I'm showing you here is my most recent one, and I've only done like 50 or 100 of them in the last year. But as the trucks get older, Ford isn't supporting them anymore. And so it's kind of picking up there.
Are there any replacements for the atmospheric pressure sensors with modern technology? We just have 8-bit parts, but you
Yes.
have to know what voltages they were putting out on the old circuit.
Yeah, but basically,
The pressure change.
yes, in this case on the old circuit, it was 0.5 volts at sea level, dropping to, I think at about 10, somewhere between 10 and 12,000 feet was kind of like the sensor's range or limit there. I've got some notes on that from a trip to Colorado, watching what it was. I got a sensor from Honeywell that I was able to put into the circuit, and with a couple bias resistors to kind of shift the voltage, I was able to get it close enough that the computer seemed to be quite happy with it.
Cool. That's recycling.
I hate seeing stuff get thrown
You
away.
can recycle aluminum can, or you can recycle a several $100 and multiple man-year electronic computer.
Yeah,
Instead of-
and this is a computer that goes in a truck that, I mean, yes, a 20-year-old truck, but, and a truck only may be worth $10,000, but the new diesel trucks are now $50,000, $60,000, $70,000 trucks, and it was like, whew, that's a lot of money.
Is most of your stuff sort of keeping that truck, 20-year-old truck running, or are you pumping performance and tuning?
I go both ways, that if, my first thing is always if it's broke, I fix it, and then after it's fixed, I start going, I wonder what I can do with this. And then that's what led to the high voltage FICMs, was like knowing how the injector worked and the problems they were having with those injectors. Stepping up that voltage step up was a huge improvement, especially with a guy with old wore out injectors, like $3,500 for a set of injectors, or $500 for a new control module. It's a
Just put a little
no-brainer.
more elbow grease on those.
Just a little more oomph to get that injector firing. And then people started reporting back that in cold weather, not Tennessee cold, but Montana and Alaska cold, of trucks starting where without the engine block heater plugged in at 10 below zero, and it was like, ooh, I didn't think about that.
Well, I want to just comment, I think you're a hacker. Incredible, beautiful, mind-blowing stuff.
Thank you. I have. Did I pass?
Yeah, you did good. For those of you that don't want to tear a board apart, you just want to know how something works, I can't recommend the old HP 3852A enough. It's a data acquisition unit. You tie off on all of the black box outputs and then tie it to the inputs, and then basically you can create your own timing chart of how the device works. And then it's a different application, but rather than trying to fix somebody else's hardware, it may not be available, you can black box it on an FPGA or what have you.
What's the name of your thing?
So like it can record it and then
3852A,
copy itself.
HP. Yes,
Wow.
and it works at real world voltages. It's kind of like a logic analyzer for the real world. So it would tie on to those voltages you got there with no problem at all. You wouldn't burn anything up. You'd have to get the right card. And it uses the old HP GPIB or HPIB, but it's the IEEE 488 bus, so you can get that bus to Ethernet, and you can actually tie these daisy chain them together and put on as many as you need, and then collect it at a remote machine.
Is that the same as the CAN bus?
Eight-bit parallel.
It's yeah, I think and you have to go back to some really old books that talk about the old what was it, the S100 bus, Joe?
S100.
S100, yeah.
100 pins.
Yeah. But that's an excellent tool if you need to do that kind of work.
Finally, if anybody here has any experience with programming EEPROMs, and especially programming ones that there is no programmer made for it, please talk to me. I'm up against a wall in some of
You
this
need to go to the
stuff.
old JAMA board forums, because they're always running into EEPROMs that are like the 21 volt jobs, and they take special codes. MCU Mall in Canada,
I've got some of their stuff.
but you need to talk to that guy, not because,
You route around it. You use a modern EEPROM.
well, yeah.
You don't program the old EEPROM. You don't try and get old 21 volt EEPROMs, 27, 16s, or anything like that.
It's true.
Or you make a computer, a 48 megahertz Arduino, that takes in that address and gives you back the answer you're supposed to get from the original EEPROM.
That's what it would take, but basically this is a proprietary microprocessor EEPROM combination made to work only with each other.
You can Google EEPROM emulator. They used to be a real thing, popular in the 70s, 80s, and you could simulate any size of EEPROM, and you would feed it with a serial port and load up some static RAM, and then it would give the answers. If you request this address, you'll get this data. and it was just, you know.
See, that's very
Look up
similar
there.
to,
That's the way they did it back then.
got this card edge connector on here, which was very convenient for giving access to disable the processor's access, processor that disables access to the EEPROM, and substitute your own EEPROM with your own code on it, a la or AKA performance chips. And that's basically exactly how the chips work, is it says, oh, you asked for this, here it is.
And the internal chip that may be bad, you can just clip the chip select lead on it and, or the output enable, and it's not even there anymore.
Nope.
It's off the bus.
You can literally solder your good chip on top of the bad chip, and that's what they do
Yes,
in the
that's
Commodore
right.
world all the time.
I'd solder a socket on top.
Okay, well, you're uptown.
Because the way these program is, they all program through the OBD2 port, which takes a serial input through the processor, and then the processor splits it out to the 8, how do you say, the 8 data inputs to the EEPROM. But the problem is, I got blank EEPROMs, but because it's blank, there's no code on it, so the processor can't boot to reprogram itself. And it was like, damn it.
Yeah, you want to steal what's on the EEPROM.
You just got.
I've got stuff that'll read the EEPROMs all day long,
Well, you get your own free.
but I can't program them. Nobody makes programmers for me.
That guy right there.
Yes.
And then one other
For
thing.
what it's worth, this is actual paying work I'm talking about. This is not, hey, I need a favor so I can make money. No, this is actually like, I need somebody who knows how to do this shit.
One other thing, if you've got a box that didn't come with the manual, but it has the FCC ID, put that in Google. FCC ID and then the number. And you may not get everything you want, but you will get insights. You'll get the name of the testing engineer. You'll get the name of the engineer who signed off on it.
Call them at home.
When it was tested, how it was tested, what its results were.
And it's the best use of the Federal Communications Commission.
Yes, it is. That is one of my favorite things.
Look up the engineer on Facebook, call him.
Hey, little bribery.
I have
fine.
found names of some of the engineers inside the code, and I have Googled up the yin yang for them. It's like back in, stuff that's probably done in like 91 or 92, so there was no internet for them to have their names on. It's like, darn.
Yeah, I love the FCC. I think so. But if you get down to that level,
For
it's a little
to make sure that no memories leave the building.
Could work either way.
And you may want to change your second symbol for the transistor on your symbol sheet, because you got an NPN when you really wanted a PNP.
It might be. I might have named them wrong.
I think that, well, that's fine, you know.
Well,
He's had 20 bucks.
he's laid the gauntlet down.
I think
That's how the internet works. You prove people wrong and they go away.
Yeah, you could.
Yeah, they're about solenoid drivers for the injector.
Oh, I know, but he said that that's a PNP.
Oh, well.
So if you're gonna call it a PNP, it really should point the
But
other
the
direction.
symbol, electronic symbol was NPN.
Yeah,
And he
both
had the
of them.
diode to ground for the inductive kickback of the injector.
You're saying you did a good job of just arguing.
That's right. They're arguing with each other, not with me. I'm
Exactly. You're not part of this conversation, sorry.
Yeah, your part is over.
Thanks so much.
Thank you all
Thank
very
you so
much.
much, Swamp. I appreciate it.
Thank you.